Alright, so we've set up our kinematic equations, and we've seen that there's two types of motions that we're going to deal with while using our kinematics. And so those are, we're either going to have motion with a constant velocity. And so if our motion has a constant velocity, then we know that the acceleration in that dimension is 0, which means that the velocity component is simply always equal to whatever it is initially. And then we have a single equation which will describe the object's motion. So I can figure out where it is at any point in time by knowing where it was initially, what its velocity is, and how long it's been traveling. Or I've got motion with constant acceleration. So here's a situation where now my acceleration has some constant value. So this is just going to be some number. Right? And so my velocity is now time dependent. My position is time dependent as a quadratic, and I have this additional equation that we saw that we can use that basically relates my velocities in my positions without time. So there's really sort of 4 equations here that we're going to need to be able to use in working kinematic problems. There's some other factors that will kind of help add to the confusion. So I may have multiple objects in a particular kinematics problem. Or I may have multiple dimensions, right? I may have something that's moving in both the x and y direction. And so the fundamental question really becomes, well, how do I make sure that I'm using the right equation in my kinematics problem? Another way to think about this is, we need to be very clear about what the limitations are for each of these equations. So if we want to sort of help ourselves out by making sure we're using the right equations in the right situations, there's some things that we need to pay attention to. So one way to deal with this is to say that, well, if we know that we're working a kinematics problem, then for each object and each dimension, then we need to ask the following question. So if I've got multiple objects, I'll need to ask this for each object. If I've got an object moving in multiple dimensions, I'll need to ask this for each dimension my object's moving in. But my set of questions will always start with the first one, which is, well, what do I know? And so basically this is going to be helping me figure out what do I know about the acceleration, the initial and final velocities, the initial and final positions, and the time between my initial and final points. Question number 2, and again this one may seem fairly basic, but it's really important, is the acceleration of the object 0? If the answer to this question is yes, then clearly I have constant velocity motion, and the nice thing about constant velocity motion is that there's really just one equation that I'm going to end up using in my kinematic problem. If the answer is no, then I need to go to a next question. So my next question becomes, well, is the acceleration constant? And again, this one seems really basic, but it's actually really fundamental. Because if the answer is yes, then I have a constant acceleration motion problem. Since the acceleration is constant, I can use one of my constant acceleration equations. But the other possible answer here is that no, the acceleration is not constant. We'll work plenty of problems where the acceleration is not constant over the motion of the object. And if that's true, then I can't use my constant acceleration kinematics equations. They'll just lead me down the wrong path. So again, to be able to use those three equations for constant acceleration, I've got to check and make sure that my acceleration really is constant over my problem. So if I know that it is, then figuring out which of those 3 equations is going to be most useful, well, the first thing I'm going to ask is, do I know or want to know time? And the reason this is useful is because one of those equations doesn't have time in it. So if I don't want to know time, or if I don't know it and think I can get away without knowing it, then 9 times out of 10, this equation is going to be the most useful one that you can use. Okay, it's our constant acceleration equation without time. If I do know time, or I know that I need to know time, then I need an equation with time. So again, there's one more question that I need to ask, which is, what do I have more information about? The initial and final position or the initial and final velocities? So do I know more about what's going on with positions or what's going on with the velocities? If I know more about positions, then I've got my position as a function of time equation. So basically, if what I know is both the initial and final position and know or need to know time, then this is probably going to be the most useful equation I've got. If, on the other hand, what I know is initial and final velocity values, and again, know or need to know time, then this, the velocity is a function of time with constant acceleration. That's the equation that will probably be the most useful. So this is just kind of a series of questions that are going to kind of help lead me, so make sure that I'm using equations when I can, and help lead me to what is probably going to be the most useful equation in solving the problem. So let's look at an example. So here's a simple example where we've got a motorcyclist traveling along a long straight stretch of highway. Initially he's traveling at a speed of 25 meters per second. The road sign informs him that he is approaching a small town and needs to slow to a speed of 10 meters per second. If the small town is only 300 meters past the road sign and he slows at a constant rate, what is the cyclist's acceleration? How long will it take him to slow down? So notice I've got sort of two questions here. Cyclist acceleration, how long will it take him to slow down? And so I'm going to start by figuring out what I know. Well, to help me figure out what I know, I'm going to start where we usually do with a physics problem. I'm going to take this word problem and turn it into the right picture. So again, here's my cyclist initially. There's his initial velocity. Here he is 300 meters further down the road, so here's his final velocity. I know that since he's slowing down, the acceleration is going to point back in the opposite direction. So again, I don't know what this value is, but I do know what direction it has to point because the motorcyclist is slowing down. And then again, if I pick a coordinate system and I'll let the origin be where the cyclist starts, then I know that the initial position vector is going to be a 0 vector. And the final position vector is going to be a vector that goes 300 meters further down the road in what I've called the positive x direction. So here's sort of, notice I've really drawn in two pictures here, one showing the initial state, one showing the final state, and that's let me figure out sort of the basics about these 5 vector quantities that I'm interested in working with. So now I can take that information and basically I'm going to put it into a table. In this case I have one object, the motorcycle, and only one dimension. He's only moving in x. So I've really only got one sort of column here that I need to worry about keeping track of. So in this case, the acceleration, well, I don't know what it is, but I do know that it has to have a negative value. So given my choice of coordinate system where the motorcycle is moving in the positive direction and slowing down, I know the acceleration has to be negative. I know initially the motorcycle was moving at 25 meters per second. Its final speed was 10 meters per second. It started at my choice for the origin, so the initial position vector is 0. It moved 300 meters in the positive x direction, so its final position is 300 meters. And then I don't know how long it took. So notice here are my two unknowns. And so I can go through and start working the problem. So in this case, for what is the cyclist's acceleration, well, I need to select an equation. And so again, the set of questions that we just sort of walked ourselves through, so here are tables telling us what we know. The next question was, is the acceleration 0? And here I know it's not 0 because the velocity of my motorcycle is clearly changing. So I have a non-zero acceleration. My next question was, well, is it constant? And in this case, yes, I was told in the problem to assume that the motorcycle slows at a constant rate. So that means that I have a constant acceleration, so I can use one of my constant acceleration equations. In this case, I don't know time. Right? So my next question of, do I know or want to know time? Well, eventually I will want to know it, but as I'm solving for the cyclist's acceleration, what I notice is that I don't know time. So what I'm going to do is I'm going to start by saying, okay, let me try my constant acceleration without time equation and see what that gets me. Well, as I look at this equation, I know the final speed, or the final velocity, the initial velocity. final position, initial position. The only unknown left in this equation is actually the acceleration. Sure enough, that's what I want to solve for. So I'll solve that for A algebraically first. I'll come back and plug in my values, and I'll get an answer with units. So notice here I've got a final answer for the acceleration of negative 0.875 meters per second squared. Okay? So two things I can check. One is, did I include the units, right? You'd hate to throw away points by simply not including the units in my answer. And again, we can go through and check and make sure that our expression here makes sense by doing the dimensional analysis to know that I'm sure enough coming up with meters per second squared as my unit. The next thing I can check is, does my sign make sense? And I've got a negative answer, but one of the things we said in setting up the problem was that we knew that we were picking a coordinate system where the motorcycle was traveling in the positive direction, which meant the velocity values were both going to be positive, but it was slowing down, so the acceleration had to be negative. So sure enough, having a negative sign in my acceleration makes sense. So there's question A. What's the cyclist's acceleration? Negative 0.875 meters per second squared. All right. How long will it take him to slow down? Well, basically now I want to solve for t, but notice I know everything else. So in this case, it doesn't really matter which of my other two equations for time I use, because I have both position values and both velocity values. In this case, I'll select an equation, and I'll happen to pick the velocity equation because it's just a much simpler equation. So again, solve that for t, plug in my values. I can check my units using dimensional analysis here, but what I get is a time of 17.1 seconds. Again, I can check, did we include units? Sure enough. And then does the sign make sense? Well, yeah, I know that my time answer should be a positive value because I started the clock at t equals 0 and need a positive answer going forward. So the last way is I can check my answer by basically saying, okay, so if I take my time and my acceleration and plug them into the other equation that I didn't use. So notice I used our equation, our constant acceleration equation without time. We used our constant acceleration equation with time for velocity. My third equation is the constant acceleration equation with time for position. I can use this to check my answer. Because basically if I go now and plug in my value for the acceleration and the time that I've solved for, do I get the correct final position? And in this case, sure enough, plugging in everything over here, calculating it out, I get that my motorcycle ends up 300 meters further down the road after when it slows to 10 meters per second, which is exactly what I know I need to get. So this is the basic way that we're going to work kinematic problems. And so what we'll do, is just to make them more complicated, is we'll work them with one object in one dimension, two objects in one dimension, one object in two dimensions. So these are sort of the layers of complication that we'll